Greetings, friends. Welcome back to the Former Farm Kid channel. And today we're going to be talking about a really great example of calculating the sector area of a circle. I ran across a great problem that really does this in essence with a twist that may be very useful for you to know. So when we get into the lesson here, it's actually going to be calculating this, what do you want to call it? Little piece of the circle, sort of banana-like looking. But before we talk about that, we want to discuss the specifics of two different types of right triangles whose relationships are very helpful to know. And the first and easiest one is the 45-45 degree triangle, which is actually in this problem what we have. In this problem, we know we aren't given any measurements. All we are given are variables. The radius here is indicated by an R. We don't have any central angle measurement, but we are given the right angle symbology. So we know that that is 90 degrees. If that is 90 degrees, we now know that this is 45 and this is 45. So the 45-45 right triangle relationships will rule on this. So what I've taken and done is taken this interior triangle and we redrawn it over here. So my two legs are R. In a 45-45 triangle, the hypotenuse is the leg distance, length, times the square root of 2. And basically that's all we know at this point. So the hypotenuse, or the base in this case to the triangle, is R times the square root of 2. I've also gone ahead and drawn in an altitude or an angle bisector to the interior triangle. Why? Because in doing this problem as a whole, we are going to need to know what the area of this triangle is. And in order to do that, we need an altitude. So in this case, I've drawn that in with a dotted line, and I've created another 45-45 within the original 45-45 triangle. And that is indicated down here. So here is this triangle right here, redrawn, just moved down, put in red so we can break it out and see how we are coming up with these other measurements. So the first and really the only two, actually I'm going to say the only one measurement we know is the base. It's the same length, so that has to be R. But now we've got to kind of go backwards because to get from a leg to the hypotenuse multiplied by square root of 2. Well, the easiest way to do this leg here is to take the hypotenuse of the original triangle and just divide it by 2. Because if this is an angle bisector, these two legs are now equal. So I'm just going to take this and divide it by 2. So it's R over 2 times the square root of 2. If you like 1/2, you can do 1/2 R times the square root of 2. If this is that measurement, this side is the same. And again, we know this is R from the original triangle. If I wanted to double check this leg, just like this leg, times the square root of 2 should equal this leg. So let's just do it. So R over 2 times the square root of 2 times the square root of 2 should equal that. And when you do the math here, simplifying, blah, 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 this is 2. 2 over 2 is 1, R. So it equals R. So again, the reason why we have split this in two again is to get this altitude without really doing any math per se, outside of dividing one side by 2 and coming up with this leg, which is equal to this hypotenuse, which is the height, I'm sorry, not hypotenuse, which is the height of this triangle right here. and we will need that. So I'm going to record that answer, and next we will look at the second special triangle, which is a 30-60 triangle. So the second triangle we're going to look at, second special triangle, is a 30-60 triangle. 30 degrees, 60 degrees, 90 degrees. These sides all have a special relationship. So basically we take whatever the base happens to be, this measurement right here, will mean this, in this case, this leg, the second leg, will be this leg times the square root of 3. So whatever measurement this is, we're going to take it times the square root of 3. And let's just say this is 3. So this side would be 3 times the square root of 3. We wouldn't calculate that value out. We would leave it as precise value, 3 times the square root of 3. For the hypotenuse, it's going to be the largest value. This is the smallest value, by the way. It's 1x. Now we are going up from the smallest, second smallest, or second largest. Square root of 3 is larger than 1. But the greatest value is to the hypotenuse, and that is simply 2x. So if this is 3, this would be 2 times 3, or 6. So those are our two special right triangles. And how can I remember all these different values? Well, it's best to, when you have a test or a quiz, don't try to recall it except for one time. As soon as you get handed your test or quiz, make a quick sketch of each triangle and go ahead and write those values out. So for the 45-45, do that one first. It's the easiest. It's x, x. And then for the hypotenuse, it would be x times the square root of 2. That's the smallest number. Now we're going to count up. Well, this one is already 1, so that's not really counting up, but we have to start somewhere. So we're going to start on the shortest leg. We go to the next number, which would be the square root of 3. So we had the square root of 2 on 45-45. Now we're going to have the square root of 3. The hypotenuse is now not a square root of 2, but a 2. So it's just 2 times the smallest leg. That's one way to remember them, and even that may not be clear to you. The easiest way is probably just to memorize them. Keep it in mind that the smallest value will always be opposite the smallest angle. The second largest value will always be opposite. The second largest value here will always be opposite the second largest angle. And the largest value here, the hypotenuse, will always be opposite the largest angle. So at this point, you may be wondering, well, okay, that 45 triangle makes sense. Why are we even looking at a 30-60 triangle? Because occasionally you will see an actual example of the central angle being 30 or 60, but be careful, and we'll talk about this one next, a 30-degree central angle. But let's use a good example here of something that may occur, and that is, how about a 120-degree central angle? Well, you can say, well, how's that going to help me knowing the special triangle relationships? Well, in this case, we would have redrawn this particular triangle over here. Remember, to get the height, we need to split this in half, which bisects this angle, which bisects this length as well. So here it is, drawn over here. And I am just going to use, again, because I can, due to the fact that 120 degrees bisected gives me a 60, 30, 90 triangle. So here again is my opportunity to save a little work for myself and just strictly fill in the values for the problem for what I know. So in this case, as we recall, the short leg here, and I'm going to indicate X because I don't know what that is, basically. I don't know what it is, but I do know that that leg times 2 equals this value. So if I set that up, that 2 times this leg equals 8, I know that the height is now 4. If the height is 4, well, the other leg then becomes that value times the square root of 3. So now instantly, and by the way, I got 8 as from the radius from the problem. We were actually given that value. So even though my central angle started out at 120, it ends at 60 when calculating the height and the length of this leg, partial leg right here. It's also going to give me the value times 2 for the whole base of the main sector triangle. So I've done a check here as well. If my calculations are correct, I should be able to plug this back into the Pythagorean theorem and come up with the one value that I do know, which is the one that was given me. So if I square this and add it to this squared, which I have said is 4, it's 4 times the square root of 3 squared plus 4 squared is equal to 64, which is c squared. So to get c, I need to take the square root of 64, and I get 8. And that would give me my hypotenuse, which in fact it is. So I know I've got my values in the correct space and the correct place. And could these two be switched and come up with the same answer? Yeah, but there again, we need the larger value opposed to the larger degree between these two. So we know the larger value is going to go opposed to the 60. The smaller value is going to be opposite the 30. Okay, so there's a good example of how a really oddball, I'm going to say, looking central angle can turn into a really easy problem, 30-60. All right, then there's another example. We look at our central angle, we go, oh goody, 30 degrees. I'm going to have another special easy 30-60 triangle. But to get the height here, what's going to happen? My angle bisector is going to turn that 30 into 15. So that is going to be a problem. In this case, and you're going to see at least one of these on the ACT, SAT, and you're going to see at least one of these on your test as well. We need to use trig to solve for instance, in this case, the base. We only know the central angle and the radius, so we've gone ahead and listed those over here. So I've redrawn this triangle, central angle triangle over here. How am I going to do this? Well, I need to know this leg. And if remember your SOHCAHTOA, sine isn't going to work, but cosine, so ca is, again, the adjacent over the hypotenuse. Well, here's the hypotenuse. There's only one of those, and there's only one adjacent leg. So using cosine, I can solve for the adjacent leg, which here I call x. And it is adjacent over the hypotenuse. So using the cosine of 15 degrees is equal to what I don't know, the adjacent x over 6, which is the hypotenuse or the radius in this case. That gives me, when I cross multiply, that gives me 6 cosine 15 is equal to x. So what does that look like? It's going to be 6 cosine 15 degrees 5.79, da, 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 da. It's an irrational number. It goes on. I'm rounding to the nearest tenth in this case. Usually problems will tell you how they want you to do that. So this length, x, becomes 5.8. Does that make sense in the context of the problem? Well, if hypotenuse is 6, we know that this leg has to be shorter than 6, but not a whole lot because this is only 15 degrees. So this is only kicked out a little bit. Has to make up very little distance to go ahead and hook up to the corner. So yeah, that problem there does. So that gives me this leg. How about this leg? Well, I can use the sine function, which is opposite. In this case, I'm going to call it y from 15. The sine of 15, the opposite over, again, the only other number we know is a hypotenuse. And this problem is done in the same way as what I've done up here. And I come up with y is approximately equal to, rounded to 1.55. I can get this total distance here by doubling that number. And if you've had a little bit more advanced trig or algebra, you could also do the law of sines for this case as well. I'm not going to go into that. That's more algebra 2, but that's possible as well. And it would give me a value for this base that I wouldn't have to multiply by 2. And by the way, when and if I should ever have to do that, let's see. Let's go back to this length right here. Let's say this length ended up being half of this leg. I would want to take the full irrational number and multiply by 2 to get the real number. So you don't want to round in the middle of your calculation. You want to use the full irrational number and then only round your final answer. Do not round in between because you are just multiplying your error, the part that you've rounded to or down. And it's just a good thing to do. Okay, hopefully that helps. Next time you see a problem like that, it's going to be no problem at all. Okay, so for calculating the circle sector, we are going to subtract the area of the triangle from the area of the circle sector. The formula for calculating the sector area is n over 360. N is this angle right here, whatever we are given. In this case, it's going to be 90 over 360. And the remainder of it is the formula for the area of a circle, pi r squared. So we are actually taking the percentage of the circle, this part, times the total circle. And that is our sector area. We're going to subtract then the area of the triangle. Sorry, it's July 4th, so the fireworks are going off. And from your 6th grade math, you'll remember that the area of a triangle is 1/2 base times height. Then let's go ahead and fill in those values. So looking at the calculation for the sector, 90 over 360 reduces to 1/4 times pi times r squared. So that is our area of the sector. The area of the triangle, referring back to earlier part of the video, again, the formula is 1/2 base times height. And it's 1/2, we calculated the base as r times the square root of 2. And the height is going to be 1/2 times r times the square root of 2. This all simplifies to 1/2 r squared. If you don't understand how this equals this, leave me a comment in the comment section, and I will go over it with you. But it basically simplifies to that. So now we do the subtraction. It's the sector area minus the area of the triangle. This is a precise value for that answer. can we go ahead and use a value of pi and get a decimal, a partial decimal answer? We can, but anytime we're dealing with pi and radius squared and square roots for that matter, we would leave it as in this form as a precise answer. The twist I was talking about on this particular question is worded like this. Write this expression in square units that represents the area of the shaded segment of C. Well, this expression does express this area right here of C, but not as square units. So how are we going to write an expression as square units? Well, to be square units, it has to be something times something else. So what we are going to simply do is we're going to factor this expression. So we have something times something else. So as I look at these two terms, what is the greatest common factor of this term and this term? Well, if you look closely, it's this whole term right here. So that goes out front as the greatest common factor. And what remains? Well, how do I go from 1/2 to 1/4? How about 1/2 times 1/2? How do I get the r squared? I've taken that out here, and I can't put it back here because that would give me r to the 4th. So this turns out to be just 1/2 pi. I haven't got that. And then for this term, it's that term right there, so it's just 1. So in this case, the twist on this answer, which you might expect to see on an ACT question or SAT, when you see it expressed as square units, all you simply need to do is factor your final answer. If your final answer is unfactorable, then you might have your final answer wrong. So check that again and see if you can make an improvement on it. Okay, any questions on what we've done here or what I've done or some of the things I've said that I need to clarify? Questions with that, just leave them in the comments section and I will certainly get back to you. If this helps you or has helped you, give me a thumbs up. Appreciate it much. Good luck.